What's up, everyone? This is Physics 2211 Lab 2 Motion of a Falling Object, and my name is Joshua Foreman. The purpose of this lab is to drop a crumpled piece of paper from rest and observe its motion falling to explore the different models of gravity versus drag force, both experimentally and computationally, and to account for the discrepancies between these models. Concepts to know. First of all, before I explain anything, in this experiment, all the forces mentioned from here on out have vectors that are strictly in the j-hat or vertical direction. That is because we're only observing the vertical fall motion of this crumpled up piece of paper. So Newton's second law is force equals mass times the acceleration vector of the object. The acceleration from gravitational pull specifically is 9.8, I shouldn't have put a kilograms there, my bad, 9.8 meters per second squared. And the drag force is associated with a negative constant times the magnitude of the velocity of the object times the unit vector of that velocity's direction. Formulas to know: the velocity update is it updates on the velocity based on the acceleration and the initial and final velocity. The final velocity equals the initial velocity times the net force over the mass, which is acceleration, times delta t, which only works when acceleration is constant or in small time intervals, which we will use small time intervals in the computational model, so that's perfect. The position update formula is similar, but its position final equals position initial plus average velocity times delta t. Okay, let's get to the tracker model. So here I am dropping a piece of paper from rest. As we can see, the graph looks somewhat linear, somewhat parabolic on the y-axis. We're not really sure if it is either. We'll explore that later with our computational model. Yeah, we don't have to worry about the x direction at all. Okay, in the computational model, we associated the mass of the piece of paper with 0.0016, but that actually doesn't matter because we are dividing by the mass in general when it comes to the forces and the velocity update formula. So the mass really doesn't matter in this experiment, but it's good to know anyway. It starts from an initial position of 1.63 meters above the ground. We decided to do our delta t in 0.0333 increments of seconds because that's how the position on the trackers were working. So g is 9.8 meters per second squared, and j-hat is j-hat. It's 0, 1, 0 of the vector. Now b, we will change that from 0.0045 to 0 for the no drag model, but for the drag model, it is 0.0045, and I found that empirically by just changing around a little numbers and figuring out the most accurate number for b to be to match up closely with my tracker model. Now this is a little harder to see, but we said while t is less than 0.933 seconds, that is because it hit the ground at 0.933 seconds. We have our f drag is the drag velocity, is the drag force. We already told you about that. The drag acceleration equals m times that. I should have put an m there, my bad. But f gravity equal, I should have put an m there. F gravity equals -1 times g times the ball's mass times j-hat. And F net equals the sum of those two. So we have our velocity update formula, which I already showed you, and our position update, which I already showed you. And we're going to get to the graphs. The graphs here, the red one is there is no computational account for the drag force. The blue one, I believe, is accounting for... the blue one has... Hold on. The blue one is the tracker model, and the yellow one is the computer model with the drag in it. As you can see, the blue and yellow are very similar. That is because it is accounting for the same forces in real life and in the computer. Now, what does this mean? When it comes to terminal velocity, when the velocity equals constant, that means that the forces cancel out, which means net force equals 0 on the system being the paper. So if we were to throw downwards, terminal velocity would not increase from before, but it would approach it faster. That is because in our formula for drag, we have the velocity affect the squared velocity affect squared speed affecting the rate at which it decelerates. So the faster you throw it down, the faster it's going to be able to slow down due to the drag formula. And I hope you enjoyed this video.